Hello everyone. Previously, we have started off with the surface processes of rock weathering, and we have discussed some of the important points related to that. And you know that there are three major weathering processes or mechanisms, which are physical or mechanical weathering, then comes chemical weathering, and biological weathering. We have discussed in detail the different aspects of physical weathering previously. I'll just go through it and then we'll begin with the next part. So physical weathering is nothing but the breakdown or disintegration of the host rock by various agents or by various mechanisms, and it doesn't involve any mineralogical or chemical change in the composition of the rock. Then there is another term which is called as erosion, and erosion is removal of these drill cuttings from its place. So erosion involves the activity or role of certain transporting agents also, like water or wind. So there is a difference between weathering and erosion. Then we have also discussed the major or important physical weathering mechanisms which involve freeze and thaw action, then hydration and dehydration, insolation, and weathering due to stress removal or removal of overburden pressure. And these different physical weathering mechanisms are characteristic of certain environments that also we have discussed. Then apart from these four mechanisms, there are other natural processes like earthquake, which can also result into breakdown or disintegration of host rock. So that is all about physical weathering. Now to begin with chemical weathering. Chemical weathering is nothing but the decomposition or transformation or breakdown of one mineral into another mineral. And you have to, and if you have to go by the definition, it is stated here, the chemical weathering involves the changes that can alter or change both the chemical as well as the mineralogical composition of the rock. So again, I'll repeat this. Physical weathering involves only breakdown of the or physical disintegration of the rock, whereas chemical weathering involves chemical and mineralogical changes in the rock composition or in the components of the rock. So the most important thing which is responsible for this is the water. The presence of water plays an important role in chemical weathering. And when you have certain gases in the atmosphere, such as oxygen or carbon dioxide dissolved in water, and when it attacks the mineral, it results into dissolving of that particular mineral or rock to form solution. So there are two main processes associated with chemical weathering. One involves the dissolving of the minerals within the rock, and other is where these mineral constituents recombine or crystallize to form a new mineral. So it is not necessary that both processes may happen in any chemical weathering reaction. You may only see the solution of rock without forming any new mineral. Or there could be dissolving of certain rock into solution and then it recrystallizes to form new mineral. So both may occur or only one process may operate. So chemical weathering, as I told you, it is associated with the presence of water. So the favorable conditions or environments where chemical weathering is operative involves the tropical and humid climates where there is abundance of water. It is not necessary that if water is not there or if water is in less amount, there won't be chemical weathering because chemical weathering can occur in deserts also. In arid environments, in low temperature conditions, you may get to see chemical weathering. So although it is more prevalent in tropical and humid climate where there is more of rain and water, it can also operate in environments where the quantity of water is less, but the acceleration of chemical weathering will be less in that condition. So when you have rainy season alternating with summers, it is the best situation for the chemical weathering to happen. So there are different types of chemical weathering mechanism similar to the physical weathering. Here the processes involve solution, hydrolysis, and oxidation. So we'll see each one of these processes one by one. So first one is the solution, or it is also called as congruent dissolution. So by definition, if you see here, solution occurs when a mineral goes into solution completely without precipitation of other substances. That means a particular rock gets dissolved by water and there is no formation of a new mineral due to crystallization. Complete solution occurs and no residue is remained there. So this happens mostly in case of soft rocks such as calcite, dolomite, gypsum, halite, and it can also happen when you have certain resistant minerals like quartz. Okay, so it is more prevalent when there are soft rocks, but certain hard rocks can also undergo solution or congruent dissolution. So what happens is uh, the rainwater or the meteoric water, when it lands on the surface, it reacts with the carbon dioxide in the atmosphere or the carbon dioxide which is in the soil. And in few cases, this reaction between carbon dioxide and water, which gives rise to formation of carbonic acid, which is shown here, is also seen to be released by certain chemical factories. But the quantity of that acidic water is much less compared to this one. So when carbon dioxide reacts with water or rainwater, it gives rise to formation of carbonic acid, which is shown here. CO2 plus H2O gives rise to H2CO3. So this carbonic acid is nothing but the liquid that you drink in the form of cold drinks like Pepsi, Coke, or Thumbs Up. So that is nothing but the carbonic acid. So you can just imagine how harmful it could be. So when this carbon dioxide is dissolved in water, the aggressiveness of the water in terms of chemical weathering is enhanced. It becomes more reactive and the rock undergoes disintegration faster. So when you have carbonic acid, the carbonic acid may also dissociate to give rise to formation of H plus ions. So when you know that H plus ions and OH minus ions, these the concentration and potential of these ions decide the pH of water, whether the water will be acidic or basic. So when you have more of H plus ions, the water becomes acidic and it results into aggressive chemical weathering. So the dissolving of carbon dioxide into water and formation of carbonic acid is an effective chemical weathering agent. So what this does, it breaks down the chemical bond between the minerals, and these rocks are dissolved into solution. So most common, you can say the prey of chemical weathering is calcium carbonate, CaCO3. CaCO3 easily gets dissolved by water, or especially carbonic water, carbonic acid. So the destruction of rock by solution depends on the water. It should not be frozen water, as it is mentioned here. Water itself has dissolving power, but it is more effective in case of evaporites. But hard rocks do not undergo chemical erosion easily when you compare with the acidic water. So it needs acid. The groundwater is acidic, and chemical weathering is usually seen in combination with mechanical weathering. As I told you previously, that mechanical weathering may result into the generation of cracks within the rock, and these cracks can further enhance chemical weathering in presence of water. So some of the reactions, important reaction is shown here. H2O, when it reacts with calcium carbonate, it results into formation of calcium ion. Ion is released and CO3 carbonate. So this is a common weathering mechanism. In terms of chemical weathering, the solution of carbonates by Carbonic acid is a common phenomena. The next chemical mechanism is hydrolysis, and by definition, it is the chemical reaction between silicate minerals and acids. So when silicate minerals react with acids, it gives rise to formation of metal cations and silica. So in comparison to solution, you see what is the difference. In solution, the water or the acidic water reacts with the carbonates. Mostly the carbonates are the rocks or minerals such as calcite, evaporite, halides undergo solution. Whereas in case of hydrolysis, the chemical reaction is between silicate minerals which are more resistant and acids to give rise to formation of metal cations and silica. So what is the difference between the two? In this case, there is no complete dissolution of the mineral. So complete solution or dissolving of the mineral doesn't take place here. Only partial uh, dissolving or solution of the host rock takes place, and therefore it is called as incongruent dissolution. Okay. In case of solution, complete solution of the rock undergoes. Uh, Therefore, calcium carbonate being soft and less resistant undergoes complete solution, and it is a congruent dissolution. Whereas silicate minerals or the minerals which are rich in silica, they are resistant and they resist chemical decomposition to some extent, and there is no complete solution of these minerals, resulting into incongruent dissolution. So incomplete dissolution is incongruent dissolution, and especially aluminum rich minerals when they undergo hydrolysis, the byproduct is in the form of clay minerals such as kaolinite, illite, and smectite as shown here. You can see the chemical reactions shown below. Orthoclase or potash feldspar, you can see when it reacts with water or when there is presence of water plus carbon dioxide or hydrogen, you get to see formation of kaolinite and silicic acid. So this silicic acid is later on transported further or may get deposited and precipitate to form new minerals or new rocks. So that is also possible in this case. Another reaction which is shown here is between albite and water, giving rise to formation of clay minerals, that is kaolinite and silicic acid. So silicic acid is the one of the products of this reaction. Now you have to remember that if there is no carbon dioxide present in sufficient quantity to dissolve and form carbonic acid, in that case the acidity of the water could be increased or may increase due to the presence of hydrogen ions supplied by certain clay minerals in the soil. So as I told you previously that as a result of reaction between water and certain gases in the atmosphere like carbon dioxide, carbonic acid is formed, and carbonic acid is more reactive agent, uh, accelerating the chemical weathering process. But when this carbon dioxide is not present, or when it is present in less quantity, the acidity of the water could be uh, seen increasing as a result of presence of clay minerals which supply H plus ions. So that also you have to remember. Now the next mechanism is oxidation. Uh, If you go by the definition, it is the chemical alteration or chemical change of iron and manganese in silicate minerals, such as biotite and pyroxene, caused by oxygen dissolved in water. Now you have to remember that whenever there is oxygen uh, involved in the chemical reaction, it is called as oxidation. So in this case, in chemical weathering, oxidation is nothing but the alteration in the iron and manganese to give rise to formation of new minerals from pyroxenes or biotite. So this happens mostly in case of silicate minerals which are in abundance of iron and manganese. So certain silicate minerals contain a lot of iron, and these iron and other minerals undergo oxidation to give rise to formation of new minerals. So one example is shown here where the pyrite is undergoing oxidation to give rise to formation of hematite. So in simple words, you can just remember that a chemical reaction which takes place in presence of oxygen to give rise to formation of a new mineral is oxidation. Okay, so this is the chart where you can see the important chemical weathering processes listed down on the left hand side. The first one is simple solution or congruent dissolution, where the soluble minerals in presence of water or water plus carbon dioxide, that is carbonation reaction, give rise to formation of carbonic acid, and the reaction is also shown in the middle column. You can see calcite which undergoes dissolution quite easily to give rise to calcium ions, as well as quartz sometimes undergoes this kind of dissolution. And you can see the principal rock materials which are affected on the right hand side. So carbonate rocks are mostly affected by this reaction to a larger extent. Second is hydrolysis or incongruent dissolution, the reaction between silicic minerals or minerals which are rich in silica takes place with water. If H plus ions are more, the water is more acidic and the reaction is more aggressive, and it gives rise to formation of clay minerals, which is important that you have to remember. So the target mineral is silicate minerals, giving rise to formation of clay minerals. And the third one is oxidation, where the loss of electrons takes place during the reaction in presence of oxygen. And the example is shown here where pyrite gives rise to formation of hematite. So the minerals which are rich in iron and manganese are susceptible to this kind of reaction or chemical weathering. So apart from these three important chemical weathering processes, the chemical weathering can also take place by ion exchange, chelation, or hydration and dehydration. So you can just remember these processes. You don't have to go into the details of this. Now, apart from this, I just want to tell you uh, how exactly the physical and chemical weathering processes operate. You can see a portion of, sorry, here you can see this area is where the physical weathering is more dominant, and the rocks and solution which is prepared is transported downslope towards the oceanward side. So this is weathering, this is erosion you can see here, and the solid particles and ions in solution are transported through the surface as well as through the groundwater. Here you can see to ultimately meet the ocean. What happens is most of the sediments which are produced on the surface, which are exposed on the surface of the earth, find their way into the sea through the rivers. And the seawater contains large proportion of sodium chloride. You know, NaCl is the dominant content of oceanic water because of its residence time, the time during which the time for which the element stays in the seawater. It is high in case of Na plus ions or Cl minus ions, and which is approximately 100 million years. If you compare this with calcium and magnesium uh, ions, they have very small residence time. It is only 1 million year to 100 million year. Because the calcium and magnesium which reaches the ocean, it is consumed by the organisms which survive in the ocean. So calcium and magnesium is consumed by the organisms, whereas Na plus ions or Cl minus ions remains as it is, or they get sorry, settled or precipitated. So here you have to remember that close to the beaches or in the shallow marine conditions where these organisms consume calcium and magnesium, they also precipitate these calcium or calcium carbonate to give rise to formation of coral reefs, which is a characteristic feature. So the solution which is transported through the rivers from the source, it is deposited in the ocean, it is consumed by the organisms in few cases, and again precipitated in the form of calcium carbonate to give rise to formation of coral reefs. Okay, so this is one important diagram that is not part of your syllabus, but I just want to show you. Here you can see one level which is marked, and it is called as calcium carbonate compensation depth. It is called as CCCD or just CCD, and it lies at the depth of 4,000 meters from the surface of the ocean. What happens is, above this CCCD, calcium carbonate gets precipitated easily. Where there is higher temperature and more of oxygen, the calcium carbonate is getting precipitated by organisms to give rise to formation of coral reefs. At the same time, if you go deeper into the ocean, as you go deeper and deeper, the temperature is less, the pressure is high, and the water is acidic. And due to this, the silica which is present in the water, it gets precipitated. So silica gets precipitated below CCCD and it is in dissolved state on the top, whereas calcium carbonate gets precipitated here and it gets dissolved when you go in deeper into the ocean. So here you'll see silica getting precipitated in the form of radiolarians or other microorganisms which are seen or observed in the form of microfossils today. So although this is not part of your syllabus, I just wanted you to know this. So this is all about the different chemical processes. You don't have to stress yourself. Just try to understand what each mechanism means and what are its byproducts. So we'll stop here for now. Thank you.